Okay, hello everyone. Today we have our session of the European Non-Associative Algebra seminar, and the speaker of today is Artem Lopatin from the University of Campinas. He's going to talk on polynomial identities for two-dimensional algebras. So please.
Okay, thank you for introduction. So the title of my talk is Polynomial Invariants for Two-Dimensional Algebras. And so this is a joint work with María Alejandra Alvarez from Universidad de Antofagasta, Chile. And so here we will work over F, algebraically closed field of zero characteristics. So I will not probably repeat it once moreover, but we always assume that characteristic here is zero. And so this talk, as you can see from its title, is about invariant theory. Invariant theory, as probably you know, is very ancient realm of mathematics, and so normally a very classical object was studied in invariant theory. And for example, invariance of vectors. We have several vectors. We have the action of general linear group over these vectors by usual matrix multiplication of matrix and vectors. And we consider some polynomial functions defined on these vectors, and we would like to find out invariant functions. Invariant means that they are invariant with respect to this action. All necessary definitions I will repeat a little bit later. Now it's just like an introduction. And so another very classical object is matrix. We may have several matrices, and we have the action of general linear groups over these matrices by conjugation. And so we may study invariance in this case as well. What I'm going to do here is consider a situation which have non-associative algebra. So this situation is quite far from classical situation. Nevertheless, these kind of problems, they have been around for a while, and some results were obtained and considered in 80s and 90s. So these kind of problems were around about 40 years, more or less. So what do we have here? Here we have A, it's some algebra of dimension D. It's important that dimension is finite. And so by algebra here I mean just vector space endowed with bilinear multiplication. So here I do not require any other restrictions on the operation, no any other properties, just algebra. And so we may consider some subgroup or group of automorphism of this algebra. Of course, the action of a group over algebra induces the action on direct sum of several copies of this algebra as follows. So here we have A plus A m times. So we have direct sum, and G acts on each of component of this sum by one and the same element G. So explicit formula is written here. We have G, it acts on first component, second component, and last component. So this action is called diagonal. And then we can consider coordinate ring of the affine variety AM. So in other words, we may consider this vector space as a affine variety. It has coordinate ring. So what is coordinate ring? It's in this case, because algebra is vector space, so then it's the ring of polynomials in variables which has indices x and indices k and I. So k here ranges from 1 to m, and k corresponds to the copy of algebra which we consider, and I ranges from 1 to d. So here d is dimension, and it corresponds to element of a basis of an algebra. So if we fix some basis of an algebra, and then we may denote like AI as coordinate of A with respect to the given basis. And then we can explicitly define xki as a function from direct sum of algebras AAA to the field F by this formula. So as I said before, this function simply takes k element in this direct sum and then takes ith coordinate of the corresponding element over the algebra. And so we may consider these variables as functions, and because of this, we may consider any element of the coordinate ring as a polynomial function. And this presentation is important for us because by doing it, we may define the action of a group G over this coordinate ring. So the definition is a standard one, and it is explicitly written here. So we have F is some element from coordinate ring. We have G is element of group G, and A is just some element from direct sum of several copies of algebra A. Then the result over the action of G over F is written here. So essentially speaking, we just consider the action of group G over argument of the function, and by doing it, we obtain the action over the function, because here we have that the field f is infinite, and then this function is uniquely defined by the way it acts on elements over direct sum of several copies of algebra A. So if, for example, we will consider quite different situation when we have finite field, then for finite field, we cannot use this definition. For finite field, we have to change this definition, namely instead of f, here we can consider just these letters, xki, and then simply expand this formula. But in case of infinite field, everything is very simple. We just use this formula and we don't have to do anything else. So because we have this explicit formula, now we can define what is the algebra of invariant. Complete name of the algebra is the algebra of G invariants of several algebras A. But for short, normally I will refer to this algebra as algebra of invariants of algebra A. So normally I will omit G because we will have G fixed, and actually we will consider when G is the whole group of automorphism, and I will omit the word several. So here is the definition. We consider those elements from the coordinate ring which are stable with respect to the action of the whole group G. Of course, we can give equivalent definition omitting this formula. So in other words, we can just embed this formula in the definition by writing that algebra of invariance consists of those elements of coordinate ring which have these properties that FGA is equal to FA for all G from G and for all A from several copies of algebra A. So in other words, what exactly does it mean? In other words, what exactly does it mean? It just means that polynomial f have one and the same value over all elements of the orbit of any element A. So we can consider any element A, we can consider its orbit, and in each point of this orbit, polynomial f has one and the same value. So we can say that polynomials are defined over the set of all orbits. And in this way, we obtain algebra of invariance. So this algebra of invariance is classical object. It has been around for around, I don't know, nearly 200 years. So it's very ancient object. And so why we need this kind of invariance? The most natural application is to separate orbits. So if we have some orbits of the action of group over any vector space, or maybe affine variety, because we may consider the same construction over arbitrary affine variety, which may also be, let's say, projective variety, and so on. And we are interested in separating orbits. So we may be interested how to give answer to the following question. If we have two elements, how we can find out are they on the same orbit or not? And another question is to give representative of all orbits of this action. So these are two closely related questions, are quite important. And invariant theory gives first step in the direction of solving these problems. Namely, in case when we have field F infinite and algebraically closed, of course, then we have that invariants, they separate closed orbits. Closed here means closed in the Zariski topology. So we have the usual Zariski topology, which is given by so the set is called closed in the Zariski topology if it's solution set of some system of polynomials. And such orbits can be separated by polynomial invariants. Of course, it's not, these are not all orbits in a general case, but for example, if we come back to the case of finite field, then and finite group, of course, then we'll see that in this case, all orbits are separated by invariants. So this particular, this case of finite fields are quite interesting and important for invariant theory. But here we, of course, not doing it here. We have field of zero characteristic. In case of zero characteristic, we cannot, as I said, distinguish all orbits by doing it, but we still can get some information, and maybe with some other non-polynomial invariants, we can hope to separate all orbits, or at least we can obtain some information about these orbits. Now, for example, everybody knows what is canonical Jordan form of a matrix is. Yes, canonical Jordan form of a matrix is. And so imagine we have one n by n matrix, and we have another matrix which acts on our first matrix by conjugation. Field is algebraically closed, and then canonical form is given by this Jordan canonical form of a matrix. So here we can also calculate invariants. Here we can calculate invariants. There'll be just traces of powers of a matrix, traces of powers of a matrix. That's it. They will not separate all orbits. Of course not, because they can be, for example, we can consider nilpotent matrix and zero matrix, and they will not be separated by invariants. But if we, together with usual polynomial invariants, will consider ranks of polynomials in matrices, then these elements will separate all orbits. And so invariants can be used, as I said, as a first step in separating orbits. Okay, and so here it was some motivation, and so now we'll continue. So now we are coming back to this our situation when we have some algebra. In general, it will be an associative algebra, of course. And now we are going to construct some invariants. We are going to construct some invariants. How we are going to do this? First of all, we are going to define operator of left multiplication and operator of right multiplication by A. Here A is some element of algebra A. And then we can define traces, left trace and right trace. So operator of left multiplication is, of course, linear map, and okay, so there was some remark that cannot see bottom of slide, but now you can see. Okay, and so it's a linear operation of a finite dimensional vector space, so it has a trace as linear operation. And so we got two traces, not one trace like in case of matrices, but two traces, left trace and right trace. And in general, they can, of course, be different. And then we will see that left trace and right trace, they're actually invariants. So what do I mean that they're invariants? So they are functions from algebra A to the field F. And it is easy to see that they are polynomial functions, which means that this trace is element of coordinate ring. And then we can come back to this definition of algebra of invariants, and we can simply verify this formula. We can simply verify this formula, and we will obtain that trace is actually invariant. When we will verify this formula, we will use the usual property of a trace. So if we have trace of a matrix A, and we conjugate this matrix by some invertible matrix, then we will the resulting matrix, of course, has the same trace. So we'll use this property to obtain that any trace, left trace, right trace, they are both invariants. Okay, and so then we can define by trace of AM the subalgebra of algebra of invariants, which is generated by all operated traces together with one. So here, what do I mean by operated trace? Actually, a little bit later, I will come back to this construction and slightly expand it, but I can briefly explain it right now. So what we can do, here we consider trace of one linear operator, but we can take composition of these operators. We can take composition of one, let's say, operator of left multiplication by A and right multiplication by B, and take a trace of it. And the resulting function is actually invariant as well, only not from A, but from A squared to the field F, but it's still invariant functions. And we can keep on doing it. And as a result, we will obviously have these two traces, but we will obtain a lot of other different traces. And all these functions, they'll be invariants. And so the algebra generated by all these functions is denoted by this way. And so there was a conjecture formulated by Artin, it's called Artin conjecture on invariants, which says that here we have equality. So here by phrase, Artin conjecture on invariance, so we say that Artin conjecture on invariance holds if we have this equality. So from this phrase, it already follows, or at least I'm hinting, that it does not always hold. So it could be that it doesn't hold. So for some algebras, Artin conjecture holds, for other algebras, Artin conjecture doesn't hold. And so now I would like to talk a little bit about history of consideration of this conjecture. So this conjecture originally was formulated and making public by Popov with the connection of non-associative algebras. So originally, of course, this conjecture was formulated for simple associative algebra, which is the algebra of matrices. And in case of matrices and group of conjugation, here we can think of it as invertible matrices. It's not equal to invertible matrices, but we can think about it as invertible matrices. And so this is very classical case, and it was conjectured by Artin that this algebra of invariance is generated by traces. Later, it was proven by Prachesy that, and by Sibirsky independently as well, that is the case. But in case of non-associative algebras, it was considered by Popov. And so he showed that in case of algebraically closed field of positive characteristic and d greater than 1, there exists a simple algebra A such that Artin conjecture doesn't hold. But in example of Popov, we always have that the group of automorphism is trivial. So it shows that, okay, this example is nice, but in case group of automorphism is trivial, we actually don't have really to study invariance, because what invariance we have here? Here, algebra of invariance is the same as coordinate ring. If it's the same as coordinate ring, of course, we may, out of curiosity, ask is it generated by traces? Algebra of our coordinate ring is generated by traces or not, but actually we already know everything in this situation. So the much more interesting situation is, of course, when a group of automorphisms is non-trivial. And in this case, I'm not aware of any counterexample. I'm not aware of any counterexample. And now we can consider two classical situations. So the first classical situation is n by n matrices. I have already mentioned it several times. So if we have matrices, several copies of them, the action is by general linear group, in this case, n by n matrices by conjugation, of course. And in characteristic 0 case, algebra of invariance is generated by traces of products of matrices. Here, we have two traces, or rather three traces, because we have these two traces, left trace and right trace, and we also have a trace of a matrix. So we may ask, what is correlation between them? So it's the same modular some constant. It's the same modular multiplication by some constant. And here we have algebra of octonions. So algebra of octonions, I think you know the definition is alternative algebra, which has dimension 8. It's simple, and it's in case of algebraically closed field, so we may consider it over real numbers, let's say. We may consider it over arbitrary field, and if we consider some general construction of it, then this algebra of octonions is obtained as a result of 3 applications of Kelly-Dublin construction. We apply it 3 times and then obtain it. So it depends on 3 constants. But if we have that our field is algebraically closed, as we have here, then we don't have to worry about this constant, because then we have, it is always split octonian algebra. It's always split octonian algebra. It has nice presentation as matrices. And so it's a unique object. It doesn't, here we don't have to write down any constant in case our field is algebraically closed. And so this algebra has a very nice group of automorphism, is exceptional simple algebraic group of type G2. It's very famous itself, this group of automorphism. And invariants, in case of characteristic 0, are known, and they once again generated by traces. So when we have octonion, we may define trace of it. It's some. So if we write down as sum of elements with respect to some basis, so it will be sum of 2 coordinates, let's put it this way. And so this octonion trace and our traces, left trace and right trace, they are not the same, but it's the same modular multiplication by some constant. And so in these 2 classical cases, Artin conjecture holds. And so it motivates us to study in case of other algebras, So now I would like to give a little bit more formalism. I would like define traces in a more explicit way. And then I'm going to define okay, at first, let me define the action in a more explicit way. And so to do this, I need to introduce some notation. So here we have our algebra, and we consider then the product of f of coordinate ring. And so then I need to consider some elements so-called generic element. We can think of this generic element as so elements of algebra A, we can think about them as vectors. So they are vectors, and we multiply vectors using a multiplication formula for our algebra. And so here, instead of elements from the field in this vector, we put elements from coordinate ring. So instead of elements of the field, we put in positions elements from coordinate ring. So explicit formula is given here. So here E1, E2, En are just basic vectors. And so here we write down elements from coordinate ring. Why do we need it? Because then we can explicitly define the action of group G over coordinate ring. Because let me come back. Here the definition was given by this formula. It's not explicit formula. So assume that we have the description of group of automorphism given by matrix, as we will have in our situation. And then we would like consider explicit action of group G over coordinate ring. Then this formula is not nice for us, because it depends on arbitrary element A, and so on. We would like explicit formula. And to do this, we introduce another notation. So we write down G black dot xk for such an element. So this symbol is not the action of a G or a xk, because xk is element from here. So It's just notation, And then for element G from this group G, or from, in other words, from a group of automorphism of algebra A, we write down G in square brackets, the corresponding matrix. So the corresponding n by n matrix. And so then here's this formula. So on the left-hand side, we have this element. What do we have on the right-hand side? Here we have matrix multiplied by vector. Matrix multiplied by vector, we can multiply them. And so, for example, to define the action of G over xk1, we consider the first element from here, it's equal to the first element from here. So here, equality of two vectors. So first element from here is equal to first element from here, and so on. And so it's very easy to use this formula to write down explicitly the result of the action of group G over elements from the coordinate ring in case elements of a group G are written down as matrices, and we know explicit form of them. Okay, and now I'm gonna define explicitly these traces, but before this, let me show some formulas. So at first, consider this algebra is denoted by this way. So it's a subalgebra of this subalgebra of this algebra generated by generic elements. So what do I mean generated by generic elements? We can multiply generic elements using multiplication in algebra A. Because when we have two elements, generic elements, here the first component of both of them is from algebra A, so we can multiply them, and the second component is just from coordinate ring. So here everything is clear. So we just multiply them as we do. So we have multiplication of a basis, and we use this multiplication tableau to multiply generic elements. And then, so we have this our subgroup G of group of automorphism. It's very easy to verify that we have this formula. It's very easy to verify that we have this formula. And then we need to consider absolutely free algebra and letters epsilon y, epsilon 2, epsilon m. So we may think about them as non-commutative, non-associative polynomials. Of course, with brackets, we have brackets in it. And then if we have A from AM, we can define the image of A with respect to this non-commutative and non-associative polynomial. Is denoted by FA. It's simply a result of substitution. And then we consider several non-commutative, non-associative polynomials. And then we need another notation. So we denote by L and R set, which consists of two symbols. So here L is a symbol and R is a symbol. And so we consider some sequence of elements from this set. So here, P1 is L or R, P2 is L or R, and so on. And then we finally can define what is operator trace. Operator trace is a polynomial function from AM to F. So it has two indices. So it depends on the sequence, ordered sequence of these elements from the set L, R. And it also depends on F1, F2, Fk. So it depends on F and P. And the formula is given here. So here, what do I mean by P with index? So what do I mean here? So I pick up P1 and see is it L or R? If it's L, then I consider operator of left multiplication. It's R, I consider operator of right multiplication. And then operator of left or right multiplication depends also on some element from the algebra. And as element of the algebra, I consider the image of F with respect to substitution. So here I have composition of operators of left multiplication and right multiplication. Of course, operators for left and right multiplication, they are associative, of course, and and then I can take trace of them. I can take trace of them, and by doing it, I obtain this map. And so here, first remark, it's not very difficult to see that the trace, which is obtained by this way, is actually a polynomial function. It's a polynomial function, so it's element from the coordinate tree. And then it is also not very difficult to verify that actually it's G-invariant. It's actually G-invariant. I am, of course, not given the proof of this statement. It's quite easy, just you have to use the definitions and that is it. And so finally, we can give explicit definition of this algebra, which generated by all traces. So we consider all the traces of this form together with one, of course, and subalgebra generated by these elements is called algebra of traces, And so now we have the following question. We have our field of characteristic 0. We have some algebra A, which is simple. And so we're asking, do we have equality or not? Okay. And so my talk is dedicated to the case of algebras of dimension 2. These algebras were classified by Ivan Kagorodov and Yuri Volkov in 2019, while actually there were some other classifications, and so it's quite an interesting question to compare some of these classifications, but this classification by Kagorodov and Volkov seems to be more complete. Its classification is given in terms of tables of multiplications of elements in algebras. It's exactly what I need, and also it has a classification of group of automorphism, which is also what we need here. Here is some list of notation is given. I'm probably not gonna look closely to this notation, so we define some subsets. No, for example, F with this indices is some subset of a field F, U is some subset of F squared, and T is given here, and notation of V here is not given. It can be found in this paper, and so V is some subset of F powered by 4. And so this should be also mentioned that these sets, they are not uniquely defined, but they can be somehow defined. We need this set because now we are going to give a list of two-dimensional algebras, modulo isomorphism. So we would like that each algebra appears in this list just one time. And so that is the reason of introduction of this set. So this classification. Okay, so at first, before classification, some remarks, and then I will show you this classification. So at first, notation of algebra is written, then the table of multiplication is written, so I will omit the symbol M, and so it's 2x2 matrix, where in position, let's say 1, 1 stands the multiplication of E1 by E1. Here, E1, E2 is the basis of algebra A. And then a group of automorphism is given. If nothing is written, then a group of automorphism is trivial, and then only non-trivial elements are written, so trivial elements are not written. I will come back then to this line. So here is this classification. So it's notation of algebra, table of multiplication, and so here is element from group of automorphism. So if nothing is written, A assumed to be any element from the field. And if nothing is written as here, it means that the group of automorphism is trivial, but it's not. So here's this complete list. So as you can see, list is quite long, and some algebras, they depend on several constants. And so here are restriction the following one. So alpha, beta, gamma, delta are any elements from the field F. Well, here actually I omitted some restrictions. So here we have some restrictions, but I didn't have space for them. So here there are some restrictions on alpha, beta, gamma, delta, and A and C are any element from the field F, and B is not equal to 0. A is different from C. And so when we have this result, it's very easy to write down explicit action of a group of automorphism over coordinate ring. And to do this, we may use explicitly given formulas. So we may come back to this formula and look at it, and we immediately obtain these equalities. Yes, we immediately obtain these equalities. So essentially speaking, what does it mean if we have xk? So it acts as we look at the first line and consider the action of element g over epsilon. We are looking on the second line. Okay. And so finally, we can formulate at first proposition and then our result. So we are going to consider simple two-dimensional algebras. Of course, not all algebras from the above given list are simples, and so here the list of simple algebras is given. So it's also quite long list, and of course it's essentially shorter than the list of all two-dimensional algebras, but we still have here a lot of algebras. And then our result is given here. So here the field F has a characteristic 0. It's algebraically closed. And we consider A is simple two-dimensional algebra with non-trivial group of automorphism. Then we have this equality in case algebra A is different from this one particular algebra. So we consider this particular case, and in this case, we actually don't know what is the answer. Do we have equality or we doesn't have equality? So this question is still open, but in all other questions and all other cases, we have equality. And so Artin conjecture here holds. Of course, this restriction that the group of automorphism is non-trivial is important, as I said before. First of all, in case group of automorphism is trivial, algebra of invariants, of course, is just all coordinate ring, and we probably do not really want to know is it generated by traces or not, because it's just a ring of polynomials, and that's it. So that is why we don't consider it. And of course, Vladimir Popov has counterexample to Artin conjecture explicitly in case group of automorphism is trivial. So here we don't consider this case. If you would consider the case of group of automorphism is trivial also, then of course we can find out here two-dimensional simple algebra where we don't have here equality. I know at least two series of algebras here. So yes, we can verify Popov result in this case. Yes, but as I said, we are not very interested in case a group of automorphism is trivial. So what also can be said about it? For example, we may consider a minimal degree of indecomposable invariance. Invariance is called indecomposable if it cannot be written as polynomial of invariance of strictly less degree. Then it's at most 2. At most 2. In some algebras, it's 1. In other, it's 2. But it's never 3. It's never 3 and never more than 3. Another remark about left and right traces. Of course, left trace and right trace, they don't have to be equal to each other. And in many cases, they are different from each other. And also, okay, let me come back to these left and right traces. So here we have left trace and we have right trace. And so, of course, we may ask the following question. Maybe it's just enough to consider just one left trace or just one right trace. And the answer is no, it's not enough in general. Sometimes it's enough, but in general, it is not. Another remark about these algebras of invariance. So if we come back to this operator trace, this general definition, so here it depends on the sequence of operators of left and right multiplication. In our case, it's always enough to take just one operator here, operator of left multiplication or operator of right multiplication. We don't have to consider compositions here. It is probably because we have dimension 2, and probably because this case is still not open. It's still open. It's we don't know what's going on here. As a final remark, I can say a couple of words about this algebra. This algebra is a commutative, non-associative algebra, and it has group of automorphism isomorphic to S3, so it's finite. It's finite group of automorphism. Its algebra of invariants doesn't have any invariants of degree 1, but it does have invariants of degree 2. So it's probably the reason it is still open. It is still open. And so as another final remark, I would like to say, so the trace function over some algebra is quite a popular object without, when we consider traces without any connection to invariant theory, and when by trace we mean just some linear map which satisfies the property of commutativity, which means that trace of AB is equal to trace of BA. And also quite often it's required that trace is associative, whereby associative, people mean that trace of AB by C is equal to trace of A by BC. Yes, so inside trace, we have this kind of associativity. If we come back to trace of octonions, then it satisfies these two properties. And people study algebras with traces from point of view, let's say, of polynomial identities and some other questions about it. Here we have another traces. Which in general, they doesn't have to be commutative or associative. And so it could be interesting to look at connection between these traces and associative and commutative traces. Assume that we have algebra and we have some commutative associative trace, or it cannot be given as operator trace or not, for example. And a list of another questions can be of interest about with the connection of traces. And about the case of positive characteristic, in case of positive characteristic, we can also do something of this kind, but in this case, of course, traces are not enough. It's obvious for matrices, for example, invariants of matrices in case of positive characteristics, they are not generated by traces. And then if you would like to do something in case of positive characteristics, then together with traces, as here, we have to consider so-called forms, or let's say there'll be coefficients of characteristic polynomial of a matrix, then maybe it could be enough or not. So case of positive characteristic with respect to invariance is always much more complicated, and so we cannot say a lot about it. So that is it. Thank you for attention.
Thank you for your talk. Any questions?
Yeah, actually, sorry. I mean, this is Lee. So a simple question. So can you compare this Artin's conjecture with the one you mentioned earlier? So it's the kind of classical Artin conjecture.
So what is your question? What is the history of this conjecture?
Yeah, you had a question conjecture earlier. Then this is another conjecture. So this is apparently more general. So how do you compare them?
Yes, yeah. Okay. Once again, what is the story of this Artin conjecture? At first, it was for matrices. So we have matrices. We have matrix algebra with multiplication, with conjugation by invertible matrices, and so the question was what are invariants, and Artin conjectured that they are traces. Yes, and then by Prochizzy and independently by Sibirsky, later it was proven that that is true. And then matrices is simple algebra, and traces are here the same as operator traces. And then Iltikov and Popov, they started to consider non-associative algebras. For example, they considered the algebra of octonions, and so the group of automorphism is exceptional simple algebraic group of type G2. We may consider, let's say, Albert algebra, which has a group of automorphism. Albert algebra is simple journal algebra, and this group of automorphism is exceptional algebraic group of type F4. And so they considered, let's say, invariants also with respect of group of type E6. And in all these cases, they had some algebra, non-associative, and a group of automorphism. And so Iltikov and then Popov, they conjectured that maybe traces is something good what we should deal to obtain all invariants. And then they remembered that Artin actually did the same in case of usual matrices. And so that was the motivation of calling this conjecture Artin conjecture, because it relates back to original conjecture of Artin. As I said, of course, in the case of arbitrary simple algebra, it doesn't hold. But if we, for example, put restrictions that okay, let me show our result. Put restrictions that group of automorphism is non-trivial, then it may still be hold. We don't have counterexample to it.
Okay. And another question. So, as you know, in this classical invariant theory, especially Weyl's work, he has this polarization theorem, right? Which kind of to say that you only need to know in your notation right here, small number of copies. You don't need to know M for all M. So is there something here as well?
Okay.
Polarization. Polarization theorem. Yeah.
Polarization theorem. Here we don't use polarization theorem, but yes, it can be used. So here, algebra of invariants is generated by multilinear invariants. Because characteristic is 0, and so this result is normally strong enough to obtain description of algebra of invariants. But probably in this case, in the case of this particular algebra, maybe polarization, yes, maybe it should be used. Yeah.
Okay. All right. Thank you very much.
Okay, thank you.
More questions?
Yeah, I would like to ask about this special algebra that you get, this two-dimensional simple algebra. You said it is commutative, right?
This one, yes, it's commutative.
Yeah. And
Its table of multiplication can be explicitly written down. For example, let me show. Okay, so here it's not very. Yes. So yes. Here's a table of multiplication. We have alpha, beta, gamma, and delta all equal to -1. So it means E squared equal to E1, E2 squared is equal to E2, and E1 by E2 is equal E2 by E1 is equal minus E1 minus E2. So it's commutative, but it's not associative.
Okay, and it has several idempotents there. Yeah. Okay.
Yes.
No, I know another algebra where the oromorphic group is S3, and it is also simple. And I was wondering whether it was this one. The paraquadratic algebra has oromorphic group S3.
Yes, here is 3. Actually, probably it's the same because it's the only one with group of automorphism S3.
Then it should be the same. Okay, yeah, that's interesting. Thank you.
Okay, thank you for the question. Maybe there are other questions. Okay, I have a question. What can you say about the algebra where this conjecture holds? How can you distinguish those algebras for which it holds and from those for which it doesn't hold? Maybe there are some sufficient or necessary conditions, but some conditions on the structure of an algebra. So how does it reflect on the structure of the algebra?
Oh, so when Artin conjecture holds and when it doesn't hold,
Yes,
that's
it doesn't hold. Yeah.
well, in my case, it's always holds. Yes, as you can see here, it always holds.
Except for one.
Well,
Except for one which we
except
don't know. Yeah.
yes, if you have, well, here we don't know. Here we don't know. Maybe it holds, maybe it doesn't. If a group of automorphism is trivial, then in some cases it doesn't hold.
Mhm.
It can be done just by digit
Mhm.
computations. Actually, I can say a little bit more. We may withdraw conditions that algebra is simple and to try to prove it for arbitrary algebra. So we have complete list of algebras, and for arbitrary algebra we may ask, do we have equality or not? Well, I started to do this, but long list of algebras is quite long, and so each algebra requires some job. But I don't have any counterexample that this conjecture may hold for arbitrary two-dimensional algebra with non-trivial group of automorphism. It may be hold, so maybe conditions that it's simple we don't need, but I don't know.
Yeah,
And
maybe you can
it's quite
replace it by
long,
perfect
yes,
example.
yes, it's quite long job because list of algebras is very long.
Okay, so yes, thank you. Okay, one more question, maybe. Okay, so thank you once again for your talk. And so,
Well, thank you for invitation.
okay. So we might stop here and see you all next week.
Okay, bye everybody.